Last week, I told you we built Nigeria's first military drone unit from scratch. What I didn't tell you was the part that nearly broke us. It wasn't the politics, it wasn't the budget, it was this. The drones we started with were built weddings. They were built to film weddings. They were the usual small drones you see around by photographers. And we needed them to work in conditions that would destroy most professional equipment. Heat, dust, wind, extended range. Reliability under pressure. Taking a consumer product and making it perform like a military asset. That's an engineering problem. Today, I'm going to walk you through exactly how we thought about it. Of course, not the classified details. We'll be talking about the engineering thinking because the principles we used to solve that problem are the same principles you can use to solve almost any engineering challenge, wherever you are, whatever you are building. The first thing any engineer must do before modifying a system is understand it completely as it was designed, not as you want it to be, as it is. This sounds obvious. It is not obvious in practice. Most people, when given a tool that doesn't quite fit, immediately start modifying it. They add things, they change things, they guess. The first thing we did was to study what we had in detail. Otherwise, any other route you take, that's the fastest route to a system that fails unpredictably. We asked 3 questions about every component. Number 1, what is the component designed to do and under what conditions? Every component has a design envelope, a temperature range, a vibration tolerance, a power requirement, a duty cycle, meaning how long it can run before it needs to rest. Consumer electronics are typically designed for controlled and moderate conditions, room temperature, low vibration, intermittent use. The second question we asked was that what are the actual conditions we need it to operate in? Now, some of these conditions, we had to write them down, we had to be specific. We know that sometimes people are not specific. You cannot say it's hot in Nigeria. Rather, it should be what temperature, at what altitude, for how long, with what vibration profile. The gap between those 2 answers is your engineering problem. Question 3. Which components are closest to their limits and which have headroom? Not everything needs to be modified. The engineer who modifies everything wastes time and introduces new failure points. Modify only what must be modified, leave everything else alone. That discipline, restraint, and modification is something most beginner engineers never learn. They never learn this. Now let's talk about the 3 engineering challenges. Once you've done the analysis and really done it, not skimmed it, you'll find that your challenges fall into 3 categories. Ours fell into 3 categories. I'm going to walk you through each one, not with specific solutions because those belong to the institutions, but with the thinking framework. The same framework applies to any systems adaptation problem you will ever face. The first challenge is the thermal management. This first category was thermal. Electronic components generate heat. Heat is the enemy of reliability. The hotter a component runs, the faster it degrades and the less predictably it behaves. Consumer drones are designed to fly for 20, maybe 30 minutes, then land. Let the electronics cool. Our operating requirements were different. I won't tell you the specifics, but I will tell you that take off, fly, briefly, land and rest was not going to be sufficient. So the question became, how do you manage heat in a system that was not designed for an extended thermal load? There are only a few answers to this question. They are the same answers regardless of what system you are working on. Option 1, reduce the heat source. Can you reduce the power draw of any component without losing the capability you need. Lower power equals less heat generated. Option 2, improve heat dissipation. Can you help the heat escape faster? Thermal paste, heat sink, airflow redesign. These are some inexpensive and often highly effective approaches to solving that problem. Option 3, manage the duty cycle. If you cannot reduce the heat or remove it faster, you manage when and how long the system runs. Operational discipline compensates for engineering limitation. The fourth option, replace the component. Sometimes the honest answer is that a specific component cannot be made to work in your conditions. Replace it with one that can. This feels like defeat. It is not. It's engineering maturity. Which option we used and in what combination? It's not something I'll share here. But those 4 questions are complete decisions 3 for any thermal engineering problem. Write them down. The second challenge has to do with signal integrity and range. The second category was communications, specifically signal integrity over extended distance and in environments with interference. Consumer drones communicate with their controllers over specific radio frequencies. Those frequencies were chosen for short range, low interference, and consumer environments. Operational environments are different. There is more interference, distances may be greater. The consequences of losing signal are not a crashed wedding video. They are something considerably more serious. The engineering questions here are: 1. What is causing the interference? You cannot solve an interference problem until you understand its source. Other radio systems, terrain, atmospheric conditions. The diagnosis comes before the solution. Second, is the problem in the transmitter, the receiver, or the medium between them? This requires completely different solutions. Engineers who skip this diagnostic step waste months solving the wrong and often ends up not even solving the right problem. The third one is: what is the acceptable risk of signal loss and what is the recovery behavior? Every system should have a defined behavior for what happens when communications fail. Not hope it doesn't happen. A design tested reliable response. I'll tell you what we found the answers to those 3 questions in our specific environment. We pointed out in a direction that required more ingenuity than money, which was fortunate because the money was limited. This is often how best engineering solutions are born, not from abundance, but from constraints. The third challenge was power and endurance. That third category is the one that consumed the most thinking time: power and endurance. Battery technology is fundamental constraint of every electronic and electric unmanned system. It was the constraint in 2015. It remains the constraint today. Every drone manufacturer in the world is fighting this same battle. The physics are unforgiving. Energy density, how much energy you can store per kilogram of battery, is a material science problem. You cannot solve it with clever software or better antennas. You work within it. So the engineering question is not how do we get more energy. You cannot. The question is how do we do more with the energy we have. That reframe from get more to waste less is one of the most mental shifts an engineer can make. This actually goes to every aspect of life. We looked at every system drawing power. We asked of each one of these drawing what it needs or what it was designed to draw in a different context. Consumer electronics are often power inefficient by design because in a consumer context, battery life is a convenience issue, not a mission critical constraint. In our context, every milliamp hour mattered. I will leave the specific solutions where they belong, but the principle: audit every power consumer, eliminate every watt of waste, redesign duty cycles around energy reality. That principle applies to any power constraint engineering challenge. Now, from what we've discussed so far, clearly you need to take a second look at your engineer mindset. I want to step back from drone entirely because the three challenges just described, thermal management, signal integrity, power and endurance, are not drone problems. They are universal engineering problems. Every electronic system you will ever build faces some version of these three challenges: heat, communication, and power. And the framework we use to address them: understand the design envelope, identify the gap, select the minimum necessary intervention, test and adjust. That framework is not military. It is not even engineering, strictly speaking. It is a disciplined problem solving. It is disciplined problem solving. Here's what separates the engineers who build things that work from the engineers who build things that almost work. The one who succeeds are ruthlessly honest about the gap between what they have and what they need. Not optimistic, not pessimistic, honest. They do not look at the consumer drone and see a military asset. They look at it and see a set of components with known performance envelopes, and they ask with complete honesty, which of these envelopes must be extended, which can be left alone, and which represents genuine hard limits that no amount of ingenuity will overcome. The last category, the genuine hard limits, is where most engineers waste the most time. They fight physics, they fight material science, they fight thermodynamics. Physics does not negotiate. The faster you identify the true hard limits of your system, the faster you can stop fighting them and start designing around them. That skill, distinguishing between a solvable constraint and a genuine hard limit, took me years to develop. I want you to learn it faster than I did, which is why I am here. What can you do right now? If you are an engineer, student, or professional, here is the exercise I want you to do this week. Take any system you are currently working on or studying. Ask these three questions. 1. What are the design assumptions baked into this system? What conclusions was it designed for? What conditions was it designed for? What are the actual conditions I need it to operate in? Write them down specifically. Numbers, not descriptions. That's your number 2 question. What are the actual conditions I need it to operate in? Write them down specifically. Write the numbers, not description. Number 3, where is the gap? And for each gap, is it a solvable constraint or a genuine hard limit? That exercise, done honestly, will tell you more about your engineering challenge than any textbook chapter. It is also the exercise I did with a box of consumer drones in a room with no air conditioning, with a problem that could not wait for a perfect solution. The conditions were difficult, the resources were thin, the stakes were high, and we solved it. Not because we were exceptional engineers, no, not at all. Though I believe we were a good team, but because we were honest about the problem before we tried to solve it. Honesty is the foundation of all good engineering. Remember that. Next week, I'm taking you somewhere completely different, away from operations room into the workshop. I'm going to walk you through how I approached designing a rocket nozzle. Components not from the textbook, but from first principles with limited resources in Nigeria. The physics of rocket propulsion, the constraints, the decisions, the parts that humbled me. If you are interested in aerospace engineering propulsion or simply how an engineer thinks from first principles, you do not want to miss that one. Subscribe to Corner Builds, hit the notification bell, and if today's video gave you something useful, a framework, a question, a different way of thinking about an engineering problem, share with one engineer who needs it. I am Colonel Kennedy Ogbole, retired. Build something this week. Thank you. God bless you.